In this lab, I observed and analyzed the motion of a stress ball that was rolling on carpet and created a model that predicted this exact motion to compare the data. Also, I observed the changes in energy of the system, the sphere, with its surroundings, the carpet floor. The results showed a very close fit of the model predicted motion with the actual stress ball motion, with a bit of error due to not accounting for air resistance in this experiment. When observing the actual motion of the ball after calibrating the length of the diameter of the ball, 0.07 meters, and positioning the axis so that we see the ball move in the positive x direction, we see a position graph x versus time form to the upper right hand corner. Using what we know about said motion and Newton's second law, I can use the fact that the net force is equal to the sum of all forces acting on the ball to predict the motion of the ball with an updated velocity and position as seen here in these two equations. These forces that act on the ball are the gravitational force, vector W, and the contact force broken up into the normal force, opposite component to the gravitational force calculated by the mass times the gravitational constant times the direction of the force, which is in the positive y direction, as well as the friction force, the component of the contact force that causes the ball to rotate and slow down and is a dissipative force. It's calculated by multiplying the coefficient of rolling friction in this specific case, which is the semi-firm stress ball on a semi-soft carpet, times the normal friction, and then times the direction of the friction force, which is in the negative x direction. Also using what is known about the energy principle, the changes in energy of this system can be observed by including all energies involved, such as the translational kinetic energy as the ball moves forward, the rotational kinetic energy as the ball rotates, and the energy lost to the surroundings, the carpet, in the form of heat, which is the thermal energy. Here, the rotational energy is calculated by multiplying 1/2 times the moment of inertia for a sphere, 2/5 times the mass times the radius of the sphere squared, times the angular velocity squared. And this angular velocity is the rotational velocity of the ball calculated by dividing the linear velocity of the ball divided by the radius of the ball. To use all of these principles and create a model, I modified the Lab 2 code and specified initial conditions of the ball's initial velocity by the first 4 positions and time points in tracker, as well as created the initial conditions for the non-changing moment of inertia, as seen here, the radius of the sphere, which is actually set to 0.035 meters, and the coefficient of rolling friction, mu, calculated by estimating the value to the closest end position of the model compared to the actual end position of the stress ball in the experiment. Also here are the initial friction force and the initial energy equations written as shown before to be later updated in the while loop. In this while loop, you see that the new motion is predicted by summing the calculated forces as shown before without air resistance, and using FNet to update the ball's linear velocity, angular velocity, and position. The changes in energy are calculated and updated and then graphed on a plot to show these changes in energy. Here you can see the ball motion as well as the gravitational and normal forces acting on this system. The frictional force is so small that it cannot be seen but is acting in the negative x direction. This graph shows the changes in energy in joules on the y-axis and over time in seconds on the x-axis of the translational kinetic energy in blue, the rotational kinetic energy in red, and the change in thermal energy in green. It is noticeable that the friction force causes the energies to dissipate towards zero, where the ball slows down and completely stops, and that the thermal energy of the ball is positive, showing that heat is gained from the friction with the carpet surroundings, but the overall change is negative of the thermal energy because the ball slows down and therefore gains less internal heat energy over time. The kinetic energies are also negative because the changes in kinetic energies are negative. As the ball slows down, the velocity becomes slower and slower, and then over time it comes to a stop, which is why these two lines go towards zero. When comparing the actual ball position to the model position, over time, the position in meters on the y and the time in seconds on the x, we see that the model almost fits the experimental graph. There is a small overprediction of the ball position later on in time, as seen here. This error is best contributed to the exclusion of air resistance in the model that had an actual effect on the stress ball and therefore caused the stress ball to slow down and go a smaller distance during the same amount of time.